Hi everybody! As promised, this is your homework video for the 3.1 Ready, Set, Go notes. So starting at the beginning, we're going to actually start with a little bit of review. The first thing we're going to review is the idea of explicit equations for linear and exponential functions. For a linear function, what we're starting with here is a slope-intercept form equation. But what I want to remind you is that slope-intercept form is just a fancy name for an equation that starts at x equals 0. So an example of an equation that starts at x equals 0 would be something like this. Y of x equals 5 minus 2x. From this equation, the key features that we have practiced finding are always going to be the starting point and the slope. In order to figure out the starting point, I'm going to look at my equation and I'm going to try to find both an x and a y. Since the x did not get adjusted, so we didn't have to add 1 or subtract 2 in order to get back to 0, we're going to go ahead and say that our starting x is 0. And our starting y value is always the first number in our equation, which in this case would be 5. For our slope, we always look at the number in the middle of the equation that is being multiplied by the x. So here's my slope right here, which means I would write that my slope here is -2. Now, a lot of times in order to help myself graph, I do like to write -2 over 1 in order to make it more obvious where I can see the rise and see the run. For an exponential equation, the way that we usually write these equations looks something like this. Y of x equals 3 times 2 to the x power. From this equation, we're still going to find a starting point, but we're not going to find a slope because an exponential equation does not have a slope. It's always going to have a common ratio instead. So from this equation, my starting point again needs an x and a y. Just like in the other equation, there was no adjustment needed for the x. It doesn't say x plus 1 or x minus 2, so that tells me that my starting point started at 0. And just like in a linear equation, the starting y value is always at the beginning of the equation. The number that we're multiplying by each time is in the middle, and that would be the 2. After I have that information, it's important to remember that we're going to make a table in order to get some points to graph for this one, because we don't have a slope that tells us how to just draw more points. So what we're going to do in the next problems, if we follow these directions carefully, is we are going to graph each of the functions. So that's step 1, graph each of the functions. Then we're going to name 3 points that are on that graph. We want to make sure that we choose 3 points that we can actually see on the graph that's in front of us. So for problem number 1, in order to graph this equation, I would try to figure out my starting point, and I would try to figure out my slope. Now this equation is written in a little bit of a different order than I normally like to write this in. I always like my starting y value to be at the beginning. So I'm going to go ahead and take this -3 and just shift it to the beginning of the equation instead of the end, which means my rearranged equation would be -3 and then plus 2x, because I'm just going to move this 2x to the end and put a plus in between. For my starting point, because there was no adjustment to make this x get back to 0, I would start at 0, and my starting y value would be -3. My slope in this equation would be +2, and again, I like to put that over 1 just to give me a better idea of how I'm going to be graphing here. When I'm making this graph, I'm going to go ahead and add some axes to this grid paper. So I'm going to put my y-axis right here in the middle, and I'm going to put my x-axis right here in the middle. The starting point tells me to begin this graph at the point 0, -3, which would be right here on the graph. From there, I would use the slope to rise 2, run 1, rise 2, run 1, rise 2, run 1, rise 2, run 1. I could also go backwards by going down 2, left 1. Once I've got some nice points on the graph, I'm going to go ahead and draw my nice straight line through those points. Now, the second part of this is that I'm supposed to name 3 points that live on this graph. We can do this in a couple different ways. We could make a table of values that show 3 points, or we could actually just make a list. So option 1 would be to make a table of values. Now I can choose any 3 points that I want. I'm going to go ahead with the first 3 points that I graphed, so these 3 right here. My first point would be 0, -3. Then my next point would be 1, -1, and my last point would be 2, +1. Option number 2 would be to make a list. So I could list my points by saying parentheses 0, -3, parentheses 1, -1, and parentheses 2, 1. Either one of those is a correct way to name 3 points that are on this graph. For problem number 2, I'm going to go ahead and graph this exponential equation. Now, just by looking at the equation, I can tell right away that this graph should be a curve because this is an exponential equation. So if I get to the end of this problem and it's not a curve, that's going to be my clue that something has gone wrong. I'm still going to need to find 2 pieces of information, a starting point and a common ratio. My starting point works very similarly to my linear equation. So if I look at the equation here, the x value is 0 because the x did not need to get adjusted, and the y value would be 27. My common ratio would be 2/3. Now, unlike my graph of my linear function, this common ratio does not tell me the rise over the run. Using this information, I'm going to make a table of values that will help me graph this equation. So the first point in my table of values is going to be my starting point, which is 0, 27. In the x column, I'm just going to count up by 1 each time, so 0, 1, 2, 3. And in the y column, in order to get more y values, I'm just going to multiply by 2/3. Now, this might be something you can do in your head, or it might be something you need a calculator for. Either way, it's okay. If I do 27 times 2/3, I get 18. If I do 18 times 2/3, I get 12. And if I do 12 times 2/3, I get 8. There we go. Using those points, I need to draw a graph that will allow me to fit those points in. So one thing I'm noticing is that all of my values here are positive, which means I'm going to draw a graph that doesn't have all 4 quadrants, but that only has the first quadrant. In order to make these points fit, I'm going to count by, 4s. So 4, 8, 12, 16, 20, 24, 28, 32. Now I'm going to label on my x-axis 1, 2, 3. So now I'm just going to graph the points from the table. So 0, 27 would be right about right here. 1, 18 would be right here. 2, 12 would be right here. 3, 8 would be right here. And you can see that my graph is starting to curve. So then I would draw my nice smooth curve going through these points, and that would be my curve. Now, just like before, we want to list 3 points, so option number 1 is just the table that you already made. If you really wanted to list out points separately, you could list 0, 27, 1, 18, and 2, 12 all separately, if that was an easier way for you to list that information. The next thing we're going to talk about in the set is kind of the idea that we talked about in the task, which is that our stories can tell us about the problem. In these problems, we're going to try to match the words to a graph, and we're going to label the graphs with the independent and dependent axis. Now, these words are just fancy words for the x and y axis. The independent axis is the x-axis, and the dependent axis is the y-axis. So your job is just going to be to label the x and y axis. So let's read the first description. Becky takes a ride on a Ferris wheel. Her distance from the ground is related to the time elapsed. Now we're going to try to figure out which of these graphs is showing us the relationship between her distance from the ground and the time that has gone by. So let's imagine a Ferris wheel. If I were to make a graph of this, my time would be on the x-axis and my distance would be on the y-axis. If I imagine a Ferris wheel, I'm going to get on the Ferris wheel, and then I'm going to go up the Ferris wheel and come down, and go up the Ferris wheel and come down. So it seems to me like the graph that matches this the best is problem number 4. Another example would be the number of hours to paint a house is related to the number of workers. So we're looking at the hours it takes to paint a house and comparing that to the number of workers. So on my graph, I would think that the number of workers would go here, and the hours would go here because I'm measuring how many hours it takes to paint. Now, if I'm thinking about this graph, it doesn't really make sense to me to draw a continuous graph the way that I did in letter A, because if I'm counting how many workers there are, it's not going to be ever 1.5 workers. So right away, I know I'm looking for a discrete graph here. Now, the more workers I have, the less time it's going to take to paint this house. So I'm thinking that if there's only 1 worker, it's going to take a long time, a high amount of hours. And then each time I add in a worker, it's going to take less and less time. So more workers means less time. That to me looks a lot like the graph in number 3. We're going to go ahead and save options C and D to talk about when we're in class. The last thing we need to talk about today is the idea of solving equations. So one of the key ideas here for solving equations is that we need to get the variable alone. So we need to isolate the x variable. The other idea is that we need to undo the order of operations, which means that when we are solving, the first thing we undo is adding and subtracting. And the second thing that we undo is usually multiplying and dividing. There are some exceptions to this rule, and we will see one example where we actually do things in a little bit of a different order, but that is in general kind of what we like to do when we're solving. So let's go ahead and take a look at just problem 7 for right now. Just like before when I was solving, I'm going to draw a vertical line through my equal sign. The first thing I'm going to do here is add 5 on both sides to cancel out the 5 that's already there, because the first step is usually to undo the adding and subtracting. So the 5's here cancel, and 37 plus 5 gives me 42. On the left-hand side, I have 3x. The next step is to undo the multiplying and dividing. So since the opposite of multiplication is division, I'm going to divide by 3 on both sides, which means I get x equals 42 divided by 3, which is 14. So that's what I would call a pretty traditional solving problem. Another example, which is a little bit of a twist on what we usually do, would be a problem like number 8. Just like before, I'm going to start by drawing a vertical line through my equal sign. But what you'll notice here is that this x plus 1 is all being divided by 2. So even though I normally start by adding or subtracting, I can't add or subtract the 1 until it's not part of a fraction anymore, which means my first step here is going to be to multiply by 2 on both sides, because that's the opposite of division. So on the left side, the 2's cancel, and all I have left is x plus 1. On the right side, 9 times 2 is 18. Now, because the 1 is not trapped in a fraction anymore, now I can subtract 1 on both sides, which means I get x equals 18 minus 1, which is 17. Now, last but not least, because many of you have probably seen that before, last but not least, let's talk about solving a problem that has an exponent. In order to solve a problem that has an exponent, we need to think a little bit differently. So, what I would start with here is subtracting 1 on both sides of the equation. When I do that, I get 5 to the x power is equal to 126 minus 1, which was 125. Now, what makes this tricky is that the x is now the exponent. So in order to figure this out, I need to try to think of a number that when I do 5 to that power, I get 25. Now, what I know, and this is what I'm thinking in my brain, is that 5 to the second power is 25, so that's not quite big enough. So if I try now a bigger number, like 5 to the third power, 5 to the third power is 125, which means the magic number for x here must be 3, since using a power of 3 gives me the desired value. Thank you guys so much for being responsible and watching this video, and I will see you in class on Friday.